Alright, 2.5, transformations of functions. We're going to do vertical and horizontal shifts, reflections about the x and y axis, and non-rigid transformations. And a transformation really is just a shifting of the graph. You're just going to stretch or shrink, shift vertically or shift horizontally and do reflections. Now the difference between the transformations are a non-rigid and a rigid transformation. In the rigid transformations we have three different types: the vertical, horizontal, and reflections. And the rigid ones keep the shape of the function or the graph, but just shifted along the axes in one way, shape, or form or another. So in the vertical shift, we can see here that we take the function itself, the outputs, and we're either adding or subtracting. In effectual, we're just shifting up if it's positive and shifting down if it's negative. The horizontal shifts are a little counterintuitive at first because you have to think about it shifting back to zero. So if we're looking at this, and you can see that the new function h is given by f of x minus plus c, the x minus c input value is going to actually shift it to the right, where the x plus c will shift it to the left. And you'll see that because what will happen is we'll be shifting it back to zero. And what we have up here is the vertex form, and I'll just put this in. It's the vertex form for a quadratic. Okay. And reflections, the first one here is a reflection about the x-axis. And the secondary one is one about the y-axis. And it's clear to see that what you're actually looking at, if you take it apart, is the output is becoming negative. Okay, so that's saying that it's reflecting about the x-axis, because at that one x you can have a positive or negative y, and the same goes for the y-axis. Alright, looking at the non-rigid components here, we have a vertical and horizontal stretch and shrink. Now when the c value is indicated above before, if we look at the function here, g of x is equal to c f of x, well, what we're looking at here is a vertical stretch or shrink. In this case, we'll have a vertical stretch when we have the c greater than 0, and we'll have a vertical shrink when it's in between 0 and 1, or some kind of fractional number. Think about that. With the horizontal, if we look at h of x now, we can see where the constant value is in relation to the function, and it's in part of its input. And if we're looking at this, then we can say that we have a horizontal shrink. So we have a shrink when c is greater than 1, because at that point the outputs will be growing much faster than the inputs will be allowed. So it'll be like this. You'll see what I'm talking about. And then if we have some fractional component here, we have a horizontal stretch. Okay. Alright, let's look at our first example of graphing via transformations. And we have g of x here equals 2 times the quantity x minus 7 squared. And like I said, this is very similar to what I was talking about earlier, in which if we have some quadratic function in x, we can actually look at this function as, that should be hk, as the standard vertex form for a quadratic. And if we didn't know this at this point, we could still do the transformation, but it does help to show that there is a vertex point here. Now, if we look at it normally, our typical graph would be set centered at 0, 0, and would increase quadratically. So if we just square each input value, we'd get our y out. So that would be our parent function. In this case, what we could see is that we're going to have a shifting horizontally and some kind of stretching or shrinking, and it looks like we're going to have a stretch, right? Because we're going to be doubling that squared value every time. So if we look at it this way, the k value, if I just write it in over here for just 1 second, the k value here would be equal to 0. So we're not going up or down, we're just shifting it left or right. And in this case, we just have to ask ourselves, what forces this back to 0? So, in other words, x minus 7 equals 0, or x has to be equal to 7. So we go out about 7 units here, and now we know that we are at 7, 0. And the graph will behave in a nice vertical stretch here, so it'll grow up a little bit quicker, in other words. And if you do want to check out the differences in the actual stretch here, it might be wise just to take a moment and take a look at it. If we looked at maybe just f of x is equal to x squared, or the parent, and we just evaluated it at an input value of 1, then we would have f of 1 equaling 1, right? If we took g of 1 now, in this case, what we have here is going to be 2 times 1 minus 7 quantity squared. And if we draw this out and actually just do the computations, then we have 2, and it looks like, well, maybe I should do it all out, negative 6 all squared, which is then, negative 6 squared. Well, that's 72 in this case. So we have this huge thing, jump from an input of 1 of the parent function to an input of 1 on the transformation of the function f to g. So quite a leap from 1 to 72. Alright, now let's look at another example. F of x here, which is 6 minus the absolute value of x plus 5. Now I've already gone in and drawn in the parent function here, which I called p of x, which is the absolute value of x. And what I decided to do this time was to just label the shifts as we're kind of like looking at them. And one of the obvious shifts that does strike out really quickly is the reflection that's actually about the x-axis. So there is a shift about the x-axis. And where did I see that? Well, I saw that right from this negative sign. And you can see that in the parent function p of x, there is no negative in front of that, which then signifies that it's going to be a reflection about that x-axis. So another thing that we noticed is that because there's going to be a reflection about that x-axis, there has to be not a minimum value, but there has to be a max value. In this case, the max value is going to be 6. So at some y equals 6, or some output, and where am I getting that from? I'm getting that from this positive 6 here. Now, whether I wrote it as f of x that way, or if I wrote it as f of x equals the negative absolute value of x plus 5 plus 6, it might be easier to see in the pink example where that shifting did occur and where that reflection does occur. So now we know that we have two major important shifts, one about the x-axis, and that produced not a minimum value like we have in our parent function, right? The min value. we don't have a minimum, we'll have a maximum, okay? And that maximum happens to be at 6. All right, the last shift is quite easy to see. It's got to be a horizontal shift, and mainly because it's contained within the absolute value bars, which obviously there isn't anything except for plus 0 in the parent. So we do have a horizontal shift. So let's put that down as a horizontal shift. And it's going to be at x equals -5. And that's because it's going to take 5 units to get back to 0, or where that value of the minimum would be. So now if we graph this out, and I'll do it in blue, we would have a maximum value at 6, but it's at an input of 5. So what we could say is that we have a vertex at -5, 6. So that would allow us to look at this a little bit nicer and maybe see what's going on. I'm going to try to draw this to scale, I guess, as much as possible. So we have 1, 2, 3, 4, 5. And we have 1, 2, 3, 4, 5, 6, it looks like. So right about here is the point, -5, 6. And now we know that it does have to reflect downward, and we know that that was our maximum point now, so it does have to go in this general direction, like that. Now, later on, we could actually find these representative zeros, right? Algebraically, what we would have to do in this case is what? We'd have to set the output equal to 0, okay? So just as a side note,